right, so like we already said, today we are going to be talking about net force. Going to be calculating net force using free body diagrams and identifying the forces on an object. So as we scroll down to the lesson, we are going to be using this PhET today to kind of identify the forces and look at net force. And then later on, you will be doing some problems. So let's open up our notebook. Let's open up our notebook and let's title it for today and get it ready for today's lesson. So today's lesson is Newton's Law 3. And we are going to be looking at net force. So we've kind of already defined force. Force is a push or a pull. It is it can cause motion or it can stop motion. But what about this concept of net? What do you think of when you think of the word net? When you think of the internet, okay, this catch of all of our attention. Okay, if we think of a fishing net, when you put that net in the water, do you take all of the fish out of the pond? No. Just the ones in the net, right? Just the ones the small portion of them. How many of you get a paycheck? Do you bring home the net pay or the gross pay? The net pay. Where does all the rest of your money go? Taxes and later on insurance, those things. So net pay is a portion of the pay that you actually earn that you get to take home with you. So this idea of net is kind of the take home part. Okay, that's sort of chemistry according to Candace version. But net can also be considered the leftover or the difference. Okay, so we will be using this idea of net force in that context as the difference. Okay, so kind of coming from that beginning there, let's go ahead and look at the PhET, and we're going to start here with the tug of war, guys. We'll reset it. Sum of forces we want, values, and we'll go ahead and have speed on there too. Now, how many of you have played tug of war before? All right, who wins in tug of war? I love this answer. That's what earlier the class said too. Me. Okay, how do you win? All right, there you go. By the stronger person, the stronger team. So if I put this red guy here and I put this the smaller blue guy, which side's going to win? The red side's going to win and if we look at this red side, what force is the red side pulling with? What? Yeah, that's what I'm circling. So the 150 newtons, it's a much larger force to the right than the 50 newtons to the left. Notice this idea of sum of forces. The sum of the forces. Now, earlier in our notes, we said that that net force was the difference. But in this scenario, it's calling it the sum of the forces. Why is that true? What is true about that or about this? Let's kind of consider. If you remember when we talked about vectors, we talked about how almost always to the right was going to be a positive number and to the left was going to be negative. So let's kind of consider that in our notebook. Okay, I'm going to go ahead and draw a little picture to remind us of what we're supposed to have. We have one guy on the left, one guy on the right. We had our rope in between. And for this scenario, the red or the guy on the right has 150 Newton force to the right. To the left, we have a 50 Newton force. Okay. So if we said that when we put these together, we're going to have 150 Newtons, that's going to be our positive number. 150 Newtons. Is 50 going to be a positive or a negative number? So we talked about that with vectors before. It's going to be it's going to be a negative number. So if I add negative 50, what am I really doing? Subtracting. Because this is the same as saying 150 newtons minus 50 newtons. They're the same thing. So either way you look at it, one of them is positive and one of them is negative because they're going opposite directions. If they were going the same direction, would either of them be negative? No, they wouldn't be. So, what is the sum of these forces that we see in our picture? 100 newtons. And you guys know that from 150 minus 50 newtons gives me 100 Newton force. Now, this number is positive. So what direction is it going? To the right. So now we have a true vector. We've given it it has a positive number, which tells us it's to the right. So our vector has magnitude and direction. All right. Give me a thumbs up if you feel like that makes sense. Okay. All right. So if we look at our scenario here, if I change and I put 150 versus 150, what do you notice about the sum of our forces? 0. So is this bucket, is this tug of war, who's going to win? Nobody. There's no movement because these are balanced forces. Okay, only with an unbalanced force am I going to get movement. So we want to keep that definition in mind. So now which side's going to win? The blue side, because the sum of our forces goes to the left. All right. I feel like we kind of got that under control. All right, let's look at the next idea here of motion. When you look at motion, and we're going to reset that so we can see it all at the beginning. I like to click all of the values so that you can kind of compare numbers when you're looking at it. Why isn't the box moving? It's on wheels. There is no force applied to it. Good word choice, good usage. So it's going to sit there until there's a force applied to it. What word do we call that? Inertia. So the same idea yesterday, we watched the video with the guy sitting on the tailgate. When the truck moved forward, the guy fell off. So same kind of concept. When I push, now let's see, if I put 1 Newton of force, is it going to move? Got a little slow, tiny movement. What if I add more? Okay, now we've got some movement. Now we've got visible movement. If I stop pushing on the cart, why is the cart still moving? Not gravity, not this time. It's a different word. Inertia. There's no force to stop it, so it's going to continue moving as long as we don't try to stop that. So it's good. I think we got a handle on that pretty well. We don't need to, for right now, we don't need to move any further with that. All right, let's look at friction. We're going to reset this so we can look at it a little bit. Okay, notice the ground changed. We have kind of a medium amount of friction. Let's kind of see what we have. We have 50 kilograms, right? If I push on the box with 50 newtons, is the box going to move? Nope, the box isn't going to move. The friction is too great to allow that to move. How much do I need to go over to see movement? 101. Wait. Now we had what had to happen in order for the box to move? You had to go over the friction force. We had to go over the amount to break that static friction to get to a kinetic friction force. Now we're going to pause here. Did friction go away? No, friction did not go away. There's still friction acting on the box. So when we took the guy away from the box before, so we stopped applying a force, what happened to the box? Really? It kept moving. It kept moving. What if I stop applying a force now? Is it going to keep moving? Let's try to get to. Okay, it's moving. What do we notice? Slows down and stops. Why? Let's look at it again. And now we got movement. Continuing to go faster, so we're accelerating. And if we take away, what is still present? Friction. So that friction is going to slow down the box until we get zero force on the box. Now, you guys, all of these things, none of these things seem like they're very like super new concepts. I feel like you guys understand this idea of friction. But what we're going to do next is we are going to draw the free body diagram of the box with the man pushing on it. So let's look at that. We're going to say, all right, net force and free body diagrams. Okay, so if I have my little man from our simulation and I have the box, okay, we said that the man was pushing on the box with 150 newtons of force to the right. There was friction on the box, and in that picture it was 94 newtons. All right, so that was kind of our picture. That was our idea. If I go to draw a free body diagram, what am I going to start with? We always start with this circle or square, either one you want to do. I'm lazy, so I pick a circle. Okay. My force that is applied, so I'm going to have 150 newtons to the right, and this is a applied force. The man is pushing on it. I have 94 newtons, so I want to make sure that my 150 arrow vector is bigger than my 94 newtons. And what was this? What force do we label this? Friction. Okay. Is that all the forces that are acting on that box right now? No. What is another force that is acting on the box? Gravity. Okay. So if I know that gravity is acting on this box, that is the force mg. What is the magnitude of gravity? What is the number that we can put on this? Well, we got to go back to our picture. What was the mass of the box? The box is 50 kilograms. So if my mass is 50 kilograms, what is the G that I multiply by? Anybody remember? It's the gravity of Earth, which was 9.8 from our lessons earlier. Okay. So 50 times 9.8 would be 490 newtons. Now, what's wrong with my arrow? If that's 490 newtons, what's wrong with my picture already? Huh? Say it again. We should have something going up. That's true. So we'll go ahead and put that in there. What's that force called? The normal force. Remember that? Because we're touching the ground. But notice this arrow. This arrow should be much bigger because 490 is a lot bigger than 150. So we want to make sure that our arrows, our vectors, are in the right ratio. All right, now we can really assess what is the net force on this object. We've thought about all of the forces acting on it. Okay. And so we need to add up these forces. All right, we saw it in the diagram earlier. But if we know that the normal force is going to equal gravity. So if I have 490 newtons up and 490 newtons down, what is my net force up and down? 0. So I'm not going to go any up or down difference. So net force equals 490 minus 490. So it's 0 newtons up or down. What about the sideways? 150 was our positive number. Minus 94, 56. What direction? To the right. And we know that 56 ends up being a positive number. So that positive number tells us that we're going to be to the right, because we set it up that to the right was going to be positive for the most part. Okay. Give me a thumbs up if you get this and this seems easy. You're good? Okay. One more example. Let's come down here again. What if I have two people? Then okay, we won't say that on the recording. And this person is also pushing with, let's say, 100 newtons onto the box. Huh? So if I push the box with 100 more newtons, what do I do with those numbers? Well, let's look at that free body diagram. We're going to have the same box. So we know that our normal force is still going to be 490 newtons. And we can see our picture kind of got a little confusing to look at when we had our drawings in there. So we have our weight, we have our normal force, now this time we have two arrows. We have 150 Newton. Well, that's too big. 150 newtons applied. And we have 100 newtons from the other guy. And then we have our 94 newtons of friction. All right, so we know that up and down is still going to be 0. But we have two that are to the right. So we have 150 newtons plus 100 newtons. And really, our 94 is negative, so we could say plus negative 94 newtons. And we know that's the same as just subtracting. So we would have 250 newtons minus 94 newtons. $156. Not very many. Does this make sense? Pretty easy. All right, let's look at the practice that you're going to have to do, and then we'll kind of determine. Let me look at the lesson today. Under here's the practice. You look, there's 2 pages, but I'm only going to have you do the first page for right now. We'll kind of do a couple of them together so that you can see. Let's look at number 1. Now, this does not show all of the forces acting on our object. All right. So what forces are missing from this diagram, from this picture? We just have a force over here that is 4 newtons. We don't see gravity. We don't see the normal force. So show me on your fingers, what is the magnitude of the net force? 4 newtons. What direction is it? Right, to the left. That is correct. All right, that one's pretty easy. All right, let's look at, let's just do a couple of them. In number 2, okay, this time we have an object with 2 newtons and 7 newtons. So somebody already said 5, so this must be pretty easy for you guys. What direction? Right. 5 newtons to the left is the correct answer. I need to stop saying right. All right, number 3. Number 3 looks like this. So our object has 4 newtons and 4 newtons. What is the net force? 0. Is the object going to go anywhere? No. So there is no net force on the object. Let's look at number 4 and be real careful of it. We have something pulling this object with 3 newtons and something pushing the object with 6 newtons. What is the net force? Are they going the same direction? So they're both going to the right. They're both positive numbers. What is our sum of forces? What is our net force? Okay, give me a thumbs up if you feel like you got this. No problems. All right. Go ahead and do, let's see. Show me on your fingers number 5. So show me a magnitude of number 5. All right, and what direction would number 5 be going? Point to that direction. All right, so do 6, 7, 8. So the rest of 6, 7, 8, 9, and 10. And don't worry about the second page. Just don't worry about the second page for right now. Do to 10. And I'll come and look in your notebook here in just a second, okay?